I'm going to talk about using IoT for smart structures. Essentially, these are wireless sensor networks, and we believe that they can increase the lifespan of transportation infrastructure and help improve safety. And I'll go into some projects that we have done. So civil infrastructure is at risk. Just in the US, for example, there's 70,000 structurally deficient bridges. This is because they've aged, but there are many factors all around the world which can cause issues with civil infrastructure. So civil infrastructure is bridges, buildings, roads, any kind of sort of civil building, civil engineering feats of construction. Sometimes there are design defects. Over time, there's metal fatigue, there's corrosion, collisions, hurricanes, earthquakes, all kinds of stresses on these systems. In fact, the American Society of Civil Engineers has, because the infrastructure is aged in the US, assigns grades to bridges, and the overall grades are pretty low because the US infrastructure in particular was built after World War II. But it's a problem around the world. As you know, bridges have collapsed in Italy and India and in many other countries as well. So what we want to do is to continuously monitor and precision target, figure out where the problems are by turning these structures into smart structures. And we believe that if we can cost effectively monitor the structure continuously, then we can identify problems and improve safety. So our first project was in Korea, actually, first major project. We instrumented this bridge with an army of sensors and got a lot of publicity in The Economist, in New York Times, and other press. And basically, it turned the bridge into a smart structure. So the bridge could monitor itself through these sensors and notify us when there was an issue. In fact, there was a hurricane during our deployment. So this was an experimental deployment, test deployment for about 18-month period or something of that order of magnitude. And what they found was that there was a typhoon that went through, and we were able to actually record the response of the bridge to the typhoon. So let me set a timer here so I know the time. Right. So this bridge was able to actually tell us how it was doing and responding during the typhoon. Sorry. So how do we turn infrastructure into smart infrastructure? As we did with this bridge, if you attach sensors to devices, objects and structures, elements that are connecting and so on, then you can tell how the performance is. So for example, in my condominium, I have leak sensors next to every sink and every appliance. And this leak sensor then can transmit data. It figures out if there is water anywhere, because I'm up on a high floor. So I don't want to cause damage to lower floors when I'm gone or something. So it sends smartphone notifications if there's any leak in the washing machine or in a sink or some pipe. These sensors may compute locally, so they may run classification algorithms or and report, unanticipated damage, extent of damage from different events. They can also network, and so in case of say the typhoon with the long span bridge, the sensors could talk to each other and see how they were responding relative to each other, and this kind of correlation can help estimate the behavior. And we, in fact, have done a research project. Much of what I'll talk about today is stuff that we've actually deployed and developed and is ready for commercialization. We also have done some research project in damping vibrations on bridges using these MR dampers, and there we would connect sensors to actuators and actually prevent damage from happening in case of typhoons and earthquakes and so on, to the extent possible. So what does a smart structure do? It can assess the structural health and risk involved. It proactively monitors the condition and the risk factors. It can allow you to then take the data, compare it with similar structures, and when there is a catastrophic event, such as an earthquake or a hurricane, it should be able to promptly estimate the damage. Now, there's a number of programming challenges in sensor networks, and these programming challenges are that these sensors have limited onboard compute capabilities, so you have to use them efficiently. You have limited energy availability in case of, for example, this Jindo bridge deployment and other deployments. We've used solar panels, and these solar panels charge the sensors, but then you have to be very careful in terms of the management of the energy. We had one deployment in Dubai, and in this case, the temperature becomes so hot that it's unsafe to charge. You only have a couple of hour window in the morning. So you have to sort of diligently manage the energy, because you can't let the energy go to zero, then you can't talk to the sensor. And you also need to be able to charge it effectively to get the sensors to work. So you have to do time management on the sensor and things of that sort. There's low communication bandwidth. You need real-time communication. Data becomes obsolete. These are some examples of sort of the programming challenges. We use a number of techniques. One of them is edge computing, because centralized algorithms are not scalable. So this allows networks can be slow, and you can be in remote areas. You might have very reduced bandwidth if there's a citywide emergency and you have got tens of thousands of installation of sensors on different structures. So edge computing also, in fact, allows you to conserve some energy, because communication can be much cheaper than computation can be much cheaper than communication. And if you're able to reduce the amount of data that needs to be transmitted, then you need less bandwidth, but you also are going to use less energy. So just to give you an example, Berkeley did a project on the Golden Gate Bridge, and it took them 10 hours to transmit 80 seconds of data. There wasn't any local processing that was happening. If you do this, then in the 10 hours, there's a huge battery problem in terms of charging it, and it could very well be that you run out of energy. In case of the Jindo Bridge, we had twice as many sensors, almost maybe 107 nodes, and what we did was to do decentralized data aggregation. So communication happened locally in communities, and then the information was transmitted and processed. So this kind of distributed computing allowed us to transmit the data within minutes. So my personal background is in computer science, and I developed the actor models, model of distributed computing, that a number of people have worked with. And this book was sort of the classic book on actors, was published by MIT Press. It's been used, my apologies, for Twitter and Facebook chat and LinkedIn and a number of other systems. And it's one of the most common used frameworks in the Orleans framework is an active framework in the Azure cloud for Microsoft. And there are languages such as Erlang and Agha, a framework in Scala. So this kind of framework allows you to think in terms of distributed computing. And in thinking in terms of this, we can develop services. These services then provide ability to put together very quickly different applications. Some services are foundational, for example, reliable communication, time synchronization, numerical libraries. Other services have to do with the network. Then there are application services for structural health monitoring, correlation functions, cable tension estimation, acceleration, displacement estimation based on the accelerations. We have a number of test utilities, and then there is essentially power saving modes and things of that sort, reporting. So we did this earliest work in TinyOS. Now we use essentially version of Unix to do our work. So I'll give you an example of a few of these services. Clock synchronization is one service. Now you have a beacon and this exchanges time, but in fact, there's an error based on sort of variations. You get a clock drift. Also, your processing is asynchronous. So even though the time of flight for a radio signal is negligible from the point of view of the millihertz that we are recording at 100 hertz or something. So we can get down to microseconds, but the operating system is not a real-time operating system because that would be very expensive to have. So there are asynchronous delays, and so that we have to develop techniques to overcome that. Clocks drift over time. If you keep resynchronizing constantly, then you're going to use up energy and take up time of the sensors. And so you can do clock drift estimations. We did frequency scaling, and the frequency scaling then, in fact, leads to sometimes losing the clock synchronization. So things have to, the frequency scaling is to save energy, and so things have to be done in a way that's carefully managing the energy to provide the right precision and error tolerance. In fact, after this synchronization, there's also database synchronization. So for example, if you have a wave going through, then you can, you're trying to correlate two sets of waves. Then you can, from sensors that are nearby, you can use the physical structure to figure out errors in the data in the time domain. And we've done that. There's fault tolerance. Large numbers of sensors means that you're going to have faults over time. And so it becomes necessary to follow these, faults and be able to cope with them. So data aggregation is another key one. So you want to process, for example, classification algorithms to compress the data instead of sending all the raw data, especially for a timely response. You can process this data, send off a response, and if data is needed for audit purposes, something, you can store it locally and send it when it's convenient, when you have enough energy or bandwidth, so on. So this means running the classification algorithm locally on the sensors. That's why smart sensors and not just sensors getting the raw data. In other cases, as I pointed out, the coordinated computing aspect, we use correlation function estimations. In the Jinto bridge, we did distributed computing. So this can create orders of magnitude efficiency. So we developed these solutions at the University of Illinois, and then we wanted to get them used in the real world. So we founded Embedded Technologies, a startup with my colleague Bill Spencer and my former graduate student Kirill Mechetov, who got his PhD with me and is working on the team. And so we've been working with these solutions now for a number of years. The project started around 2001, 2002 timeframe at the university, and a decade later, about 14 years later, the last 6-7 years, we've been increasingly commercializing different solutions. And some of these images, the images you see here are in fact some of the deployments we've had. So pairing real-world experience with the SHM research. So what is the goal of IoT for structural health monitoring, and what is the value proposition that you would want a startup to do? You want to predict structural problems using real-time and historical data. This is something I hinted at right at the beginning of the talk. You want to prevent damage, so preventive maintenance, figure out where there might be potential damage or weakness. And this will help you enhance safety. So if you are monitoring continuously, you can send notification to engineering personnel or whoever the gatekeeper is, the traffic engineers and others. And by providing an expedited response, you can also say, okay, things are safe after a catastrophic event, or things are not safe, because inspecting every structure after a catastrophic event, if it's a widespread event, is a very labor-intensive process that can take a very long time, and basically shut down important infrastructure for your transportation requirements. So some of the examples of deployments we've had are rail and highway bridges. the world's largest Ferris wheel. Any large structure, as you will see, can, in any large physical structure, we can instrument that has a vibration or strain or other sort of sensing that can tell you that there might be a problem. So during construction, they instrumented this Ferris wheel, for example. The Jindo Bridge that you see, a bunch of other bridges we've done. One of them is shown on the left, train bridge in this case, truss, both wooden and steel. And we've also instrumented buildings for earthquake damage, in this case, in partnership with Zurich Insurance Group. We have a global partnership that we're working with. So what is the technology? Well, the technology has got several parts. There are sensor boards, and these sensor boards are getting acceleration and certain other things like temperature, humidity, light, and so on. So you can adjust your readings, sensor readings, based on local conditions, which can affect it. For example, if you were trying to get the cable tension, you know that the temperature is going to affect the cable. And so knowing the temperature locally at that point is important, and the sensor can help you do that. We have also developed data acquisition boards, strain gauges, pressure sensors, and we can provide these readings. So there's this hardware that's been developed, customized hardware, and this allows us to do wireless communication through this hardware, through a radio board, and provide high fidelity monitoring and data acquisition. So essentially, there are 6 steps to our process. You take the wireless node, so you don't have issues of wiring, install them on a structure, and these can be installed via magnets or screwed in if the structure allows. Obviously, in a bridge, they don't want us screwing in things, but we can use magnets that attach to the steel structure. Then we use data synchronization schemes and high fidelity distributed sensing. Sensors can measure acceleration, strain, etc. We process this data to create semantic information, analyze the results, and then if there are anomalies, we send notifications to the right parties. So that's the basic idea. And here are the 2 types of measurements, things that have to do with the statics, temperature, humidity, light, compass, things of that sort, which do not depend on the motion or changes in the structure, in the movement of the structure. And then there are other which have a higher sampling rate, more hertz, more data, things like acceleration, strain, and so on. Wind velocity was something that we were recording locally, and in fact in the typhoon, so we knew exactly how much wind hit that bridge in Jindo. So monitoring structural safety, basically you look at the physical structure, and every physical structure will have modes. These are natural frequencies of movement in various dimensions. So if it's a building, you'll have these 3 movements. If it's a bridge, you'll have up and down movement as well. Buildings are fairly grounded, so up and down movements will be relatively minor. So these, in response to any excitation, you'll have these physical movements. And then from these movements, you can make estimations. So in case of a cable-stayed bridge, which you do not want what happened in India to happen anywhere, a very tragic event with the collapse of the Morbi Bridge, which had just been repaired. You had these cables. And so if in case of the Jindo Bridge shown above, we in fact took sensors and put them on every single cable. So we could monitor the cable movements, and then from that estimate the tension and see if it was within the specs and if things were responding as they were supposed to. So you build a model of the structure, and in terms of, in this case, the cable tension has a simple model and specs, and you can see if things are following the specs. Then there's more complicated models made of the individual elements. These elements you can build computationally, the dimensions, the mass, stiffness, and they do this as design time. Based on the structural plans, though, what actually happens may not reflect the behavior of the structure. So we don't know for a fact, but I imagine the engineering firm, the design firm that planned the Morbi Bridge had certain estimations of the cable tension, of the weights that would go on it, and how the movement would be. However, the reality can be quite different. So because of flaws in the construction or whatever other issues that might arise, poor materials or weight limits that have been are getting exceeded, you can have behavior that is not accurately reflect. The model does not necessarily reflect what the structure is. So what we do is then we can do the dynamic excitation. We can see with wind or train crossing or earthquakes, we can simulate what the response should be and see if the model is true to the structure as it's built. So what this does is to allow us to update the model and say, okay, really what the bridge is doing is the following, or here are the issues, or with the building, it's not behaving as it should. It should have been more rigid, or it should have been less rigid. And so in response to just a high wind, for example, its behavior is not what it should be. And these are what the model parameters instead look like. And therefore, you can propose things that say something about the state or the condition of the bridge. So we can do this at any point in time, look at the displacements, look at the measurements, and we can track changes over time. So this could be periodic measurements. It can be event-triggered measurements, and then look at significant events that are changing how things may behave. So these significant events can cause dislocations, and these dislocations in the structure can then be detected that there are issues that have cropped up. You have to correct for environmental and location-specific factors. So I mentioned already, for example, the temperature will affect how the cable is behaving. So these kinds of factors, if sunlight is shining or things of that nature, seasonality, they will have an effect. Now, energy, as I mentioned, is a key factor. So let me give you, and this will lead to the final example that I will present in my talk. You have events that are being triggered, but you cannot afford to, that you want to sense in response to, for example, the typhoon, or if there's an earthquake. We've had sensors when there's an earthquake, and we said what the response of the structure was. We have deployments in Mexico City, for example, and there are frequent earthquakes there, and we then can say how the structure did. So if you have the sensor on continuously, then you have to power it. But some of the deployments will be out where there is no source of AC power. Even if there's no source of AC power, some earthquake could wipe out a station, or other reasons, hurricane could wipe out a station. And then you want to go into a mode where you're not sort of constantly having the sensor on, because it will consume power, and within a few hours, you won't have any sensing capability. So what we have done is to create a low power trigger sensor. And what this low power trigger sensor does is to continuously record data. So this data is just recorded for a small amount of time, some say 80 milliseconds. And then it's a continuous buffer, so it doesn't store the data. So it's not talking to the processor, it's simply recording. But it can look at detect the activity. So if there is some anomalous activity, for example, a hurricane, earthquake, wind, collision, whatever, depending on the thresholds that we've set, it's therefore a programmable event-based switch. It wakes up the processor, and it feeds it that window of data that it has taken into the main processor, which can then proceed to do its analysis. So this way, we don't miss any of the data that's being recorded. So this small window then wakes up. So the data from this trigger accelerometer, and then the high fidelity data. So we get this triggering behavior. So we do this, and we've used this then in railway bridge monitoring systems, for example. So if a train is coming by, you want to trigger the accelerometer, it's in the middle of nowhere, and say, a train is coming, let's start recording and see what the response of the bridge is. So one case study, for example, was this autonomous system to record the rail bridge behavior of the railway bridge with wireless sensors. And, of course, then if something happens, then you would trigger the emergency response. So in this case, we also use strain sensors. What strain sensors can do is tell us about the track condition, because you can then measure what the strain is. If there is some issue with the wheels, what they're doing, you'll have the vibration data as well as the strain data. And in fact, you can even measure the load of individual train cars as they pass by. If it has been inaccurately recorded in the manifest, for example, you'd be able to detect it. You can see our sensors, the blue boxes on the ground there, and in the box on the left. You can also see the solar panels. So there's the installation. This installation was done on a commuter rail line in Chicago, where we are situated. And so the behavior of this is, as the train is going by, the accelerometer is triggered, and then you can record, in this case, it shows you the shear strain at the Calumet Bridge, just outside the bridge. The recording is being done. And this then tells you what the force is on each structural element. So you have these sensors all along, and you can tell what forces are being applied and how the bridge is responding. So here's an example of a different steel truss bridge. And we have marked in red places where we were doing recordings. And then we found that there were some members, which you can see on the bottom right, marked in red, which actually looked like they were had issues from the data, from the sensor data. And in fact, the inspection report showed that the truss on the west side of the bridge had multiple members with section loss, and the east side had no loss. So we could compare the data of the two sections and say, here there's problem. There's a 15% loss, 40% loss, 15% loss, and that then tells you exactly where to reinforce it. And this is being done continuously, so we can tell what's happening. So we can look at the displacements over time and see if they go above a certain level. Green means everything is fine. Yellow means it's in a problem zone, and the red zone, or I guess it's showing up in my screen as pink zone, means that it's dangerous and things should perhaps be shut down and so on. So we take multiple measurements, we use statistical methods, and we can compare different behaviors of behavior of the bridge on different sides, and use symmetries and a number of techniques. Now, the final example that I'll give, also related to bridges, is overheight vehicle collisions. So overheight vehicle collisions are a critical problem all around the world. So if you look at the bridge failures, and I think the study was done in the US, 24%, the estimates were that 24% of all bridge failures are caused by vehicle collisions with the bridge. Of course, this also happens with river bridges, where barges sometimes collide into the bridge's columns. 50% of the bridge closures are also caused by overheight vehicle collisions. And when there is a failure, it can shut down a transportation artery for many days. So on the Lakeshore Drive, which is a major artery in Chicago, US Highway 41 runs is the official US highway name for it. It was closed for a period of time just by accident, because some people who were working on the lights, they saw a damage to the structure there. And if it hadn't been seen, it could have led to a catastrophic failure. it had been inspected, so the inspections are every 2 years. Whereas if you're monitoring, we'd be monitoring continuously. In this case, just through serendipity, just because the workers happened to be there, they noticed that there was a problem with the structure, and they had to close down this highway for many days to repair the bridge. So, so it's important to sort of figure out what's happening. Now, of course, when you have a bridge, for example, it might have train crossings on it and traffic underneath. It can have impacts. The impact can be significant. The impact might not be significant. It might be a small scrape. And you have to, of course, distinguish it because the bridge will also vibrate if the train crosses. And then you want to notify about the event, how significant it was, if something just touched it and stopped, if something hit it hard, if something scraping it back and forth, and so on. So this is a global problem, not just in the US. So there's examples of the US. I was vacationing in Ireland a few years ago before the pandemic. And here was a sign in Dublin. If you strike this bridge, please call this number, which is above in Irish, and call the control room. Now, the problem is that when they do this, somebody has to go out and look at the bridge, which can be expensive. And sometimes they don't report it. If they go out and look at the bridge, sometimes the hit is not very significant. So it's taking up time, precious inspection time. If the hit was significant, the delay in going out and inspecting it and then closing it and so on is can lead to a safety catastrophe in the interim. So you basically have this trade-off and a problem, and quite often truck drivers or whoever will not call. And the reason is basically because they don't want maybe to slow down or hassle or feel like they will be held responsible. So they just sort of back up and leave, and that's quite typical behavior. So we want to know the intensity of the collision, what happened to the structure, and when it happens, and how urgent it is to inspect the bridge. So here was an example of what we did. CN railway engineers deployed 3 Embedor sensors on a Class 1 bridge. This is an overpass that you can see vehicles go under it. It was in Chicago. It's a low clearance bridge, fast moving traffic. There's some evidence of impact. In fact, you can see this beam here, which has been installed to sort of try to get the impacts before they hit the bridge, but obviously that still shakes up the bridge. It turns out that even within seconds of the installation, 3 vehicle impact events were detected and reported to CN. CN is a major railway in the US, what's called a Class 1 railway. It's one of the 3 major railroads. So this was very effective. So here's an example of the kind of classification that had to be done to make this effective. You have train crossings. You can see the impact accelerometer on the left. It detects the impact. The event accelerometer comes on. That's the top right. And then we compute the event displacements with what the impact of the event is. So this is with the train crossing. Then there's a cluster of events here. And we could analyze it and realize a truck got stuck on the bridge and then tried to get unstuck. So it caused this cluster of events every time it sort of scraped. There's another weak impact. So this is within a few days of each other. I don't have the date on the first one, but it's within a few days. And here you can see the scrape, we can see the intensity, we can see the impact acceleration, and then we can see how the event unfolded on the bridge, how the damping effect was, and how the bridge was responding to it, how much displacement it had, and so on. And so this kind in all 3 dimensions. So the different colors here are the X, Y, Z axis. So so these events then can be classified, their intensity can be determined, and I believe every bridge in any city should have these accelerometers on the bridges, because if it has an underpass, traffic going underneath it. So I'll conclude here, since I'm at the end of my time. allow for a few questions. So I believe IoT for smart structures can save costs, enhance safety, extend the life of the structure. It's relatively inexpensive. I haven't got into the cost, but you can do incremental deployments, and you don't have large connection charges and wiring issues. We can do large-scale deployments, and so collaborations, partnerships, service agreements, research partnerships, all of that is welcome. Thank you.
All right, thank you so much, Gu. That was an interesting talk. And we do have some time for questions, just several minutes. And I guess I'll just start with one question. So I see you have deployed this in several different countries. I guess lots of these transportation infrastructures are kind of different. Like when you actually detect these issues, is the learning sort of like transferable, or you have to train every time for a different bridge, for example, that you deploy this?
Yeah, so there's different kinds of things. So in terms of the impact detection, you can tell exactly what the impact is.
Mm-hmm.
And engineers have a good idea about what the bridge should be able to sustain.
Okay.
In case of condition monitoring, it's a different story.
Yeah.
So in terms of condition monitoring, you need to, well, with railroad tracks, of course, again, it will be fairly standardized, except on the bridge. So in terms of condition monitoring of a bridge, um, some things are relatively simple models like the cable tension. But in general, you'll have to build an FE model of the structure and then compare your sensor readings to the FE model, see if it's meeting the design. If you're lucky enough, sometimes you can get the design parameters. So for example, when we did a project with Zurich, we were able to in fact get the model itself that the architects had used. And then we could compare our sensor readings to that model and update and see if the building met the specifications. So in these cases, you can build an FE model. It's not that hard to build an FE model. There are packages. Well, you of course have to know something about the materials and the connectivity.
Yeah, yeah.
But there'll be specific types of bridges, and then you can compare. So, some things will be obvious. So impact detection, kind of, you can at least tell the intensity of the impact. Other things you will get a good idea of because you have used it from one deployment to the next. In other cases, you have to build a model or sometimes just symmetries. So in case of that truss bridge I showed you, it had two sections, east and west section, and you could see the difference.
Mm-hmm.
And now, of course, you have to know a little bit about the soil condition and figure out what the difference might be. But if you have some knowledge of the structure, you could say, okay, this side is looking very different than this side. Or there are five sections here. One section is behaving very differently, but the amount of force on it should have been quite similar. So of course, this needs a domain expert. I, as a computer scientist, would not want to make, well, I would look at it and say it's different, but the domain expert would look at it and say, okay, yes, it shouldn't be that different. So some things will be obvious. Then, of course, I mentioned historical data. So you could look over the years how things are changing, and if you have deployed it, for years, you'll see from one season to the next. Next winter, if it's very different than what it was last winter, you would start to wonder. And then finally, of course, there'll be big data.
Yeah.
So the cooperation with, say, an insurance company, their interest, you can imagine, would be, and I don't want to speak for Zurich, I don't, but it's a large insurance conglomerate. But for example, if you manage assets, you're a city, you've got hundreds of bridges to manage, then you'll get big data and you might start to say, okay, can we figure out something from this that we did not know before?
Yeah.
And look for patterns. And that stage we're not at. We don't have hundreds of deployments at this point, but hopefully soon. Right.
Yeah, hope so too. So for the energy challenge, have you considered using solar power, for example, or?
That's what we did for in the deployments out in the field in the train tracks. You saw the sort of the solar panel, and even in the case of the Ferris wheel, which is like the cable tension bridges. And in case of Jindo Bridge, we use small solar panels with each of the processors, and then the processor controls the charging because you don't want to overcharge, you don't want to let it go to zero, and then you have to do aggressive energy management and be conscious of how often you're recording and what you're recording and how much energy it's consuming and what the battery capacity is.
Okay. All right, so any other questions from the audience? Please feel free to unmute yourself or use the chat if you have any questions. Okay. It seems like I don't see any questions coming from the chat. I guess that's the end for the first talks. Thank you so much, Gu. And
Thank
we
you.
can